Great, recording is rolling. So, welcome to Thursday, December 2nd. So, I do have your guys' last quiz of the semester clipped to the side of your desk. It looks like this. You guys see on the right side of your desk, it says Rotational Dynamics Quiz Honors. You guys got that? Right. So, let's have this due a week and a half from now on Monday, December 13th. So there'll be plenty of time to do this, right? You guys got not this coming Monday, but the Monday after that, right? So plenty of time to do this one. Right? Right. So remind you guys that let's look at all these bullet points. This one ignore, that's just for my AP kids. But we're doing some textbook problems. Actually, we'll finish these today. The textbook problems that I assigned you guys, right, these right here. We'll finish the main ones today. Now those are due Friday, not tomorrow Friday, but 1 week from now. So again, like plenty of time. If you guys ever want to turn anything early, feel free to. I mean, we're finished these. Plenty ahead of schedule. I do want to mention too that I don't have access to my grade book still yet. There was some weird technical thing going on. I'm talking with the tech office. They're working behind the scenes, so I haven't been able to put in any of your lab grades or any grades for that matter, or even see them. So just so you guys know, in case you're wondering, like, why aren't any grades being added? Okay, so I told you guys this new quiz due a week and a half from now Monday. Okay, and then I think I threw this link on the board the other day too. One of my students, Cooper Baskell, is in AP Capstone. He's doing this research survey. There's a question, takes a few minutes. It's on palm oil. So if you could help him out with that. And he does need this by Friday if he did want to try that out. So that would help him out. So, right now, yesterday I gave you guys a torque lab, and I was thinking about this after the fact. Deal with that torque lab is I always redesign it like pretty much every year, and I don't know, I can never make it quite like I want to because I think there's like some pretty basic fundamental like concepts that like are definitely graspable. But in retrospect, I think the lab I gave you guys today was maybe like a bit more complex than I meant it to be. So let's solve this problem here, which actually looks a lot like you guys' torque lab setup from yesterday, or the second setup from yesterday, but maybe a more simplified version of that. So if yesterday, I mean, obviously the reason I give you guys labs or like any assignment is so that you can get something out of it, right? If what we did yesterday, hopefully you did get something out of it, but if you didn't quite click, like this is just kind of confusing, hopefully this right here clicks and get a concept out of it that I want you to get out of it. Right, suppose we have this scenario where there's, say, a meter stick on this pivot point at its own center mass, right? Could like pivot here. And there's one mass of known quantity. Let's say we got 100 gram mass. 100 grams, that's like this guy right here, 100 grams. Right? And we got some other lab mass that maybe we don't know what it is, right? It's in some unknown quantity. Right? And we're sliding this back and forth. And if you slide it too far to the left, this whole thing tilts this way. You slide it too far to the right, this whole thing tilts this way. But if you park it right there, then right at that point, this thing just goes into equilibrium. Now, it's not really stable, but it's just like, yeah, kind of like the second setup you guys did yesterday. Right? Can anybody look at that and tell me what the value of that second mass is? Does anybody know? Yep.
Is it 200 grams?
It's 200 grams. Okay, yeah, you guys get this. 200 grams, right? Because relative to this pivot point, you guys see that the fact that it's half the radial distance compared to the small mass, right, means it has to have twice the weight, right, to balance the torque. Right? See, the torque about this middle pivot point, right, we got the 100 gram lab mass is trying to cause a counterclockwise torque. The M2, whatever that is, well, actually, you guys know now it's 200 grams, right, is causing a clockwise torque, right? Right. So, of course, weight, the force is actually mass times gravity, but same gravity field, right? So, yeah, so we got like 100 units down times 10 centimeters. Isn't that like 1,000 units of torque? Right? So something to do with that, right? Cut through the gravity field. Right? And then over here, well, you also need 1,000 units of torque, just the opposite way, right? Clockwise instead of counterclockwise. So yeah, you need 200 grams. That's the only number it could be, right? Or maybe like bigger picture in terms of proportions. Again, the fact that it's half the distance from this pivot point means it has to have twice the weight and therefore twice the mass. Just a proportion thing. Right? In fact, maybe I should have had you guys do a more simplified setup like this yesterday in your lab, so that see if you put the center of mass of the meter stick itself at the like the most obvious pivot point, make it like an actual like pivot point, right? Then see the meter stick itself doesn't actually add any torque to the system because it just balances out, right? Right. All right. Thanks for that. All right. Oh, next thing. Let me switch my screen here. Let's see. Well, no, present screen to share. All right. Got this RPM comment. I talk about so let's do with oh, let's read this and then go into let's see. Playing a record. Let me show you something interesting. Compare a point on the label. They're talking about those old records from like many decades ago, right? The actual physical records. Right? Compare a point on the label with a point near the record's outer edge. They both make a complete circle in the same amount of time, right? So it's rotating at some rate. Right? Yeah. Right. Okay. But the point on the record's edge has to make a bigger circle in the same time, so it goes faster, right? It goes more distance in the same time. See, the 2 points on the disc move at 2 speeds, even though they have the same revolutions per minute. Huh? Wait, they got 2 different speeds, even though they have the same speed? What's up? Because he's talking about 2 different concepts. He's talking about linear speed versus angular speed. Right? Now, when he talks about the record spinning at say it takes the same time to make the same rotation, same revolutions per minute. What kind of speed is he talking about? Linear or angular?
Angular.
Angular, yeah, that's like a rate of spinning. Versus when he's talking about the needle moving across the surface, right? Think about that needle moving, like making a point of contact, right? Its linear speed actually is variable. So let me switch back over here and draw this out for you guys, and then tell you guys a little bit about modern CDs and how that actually differs from the old technology. So there were these old records, right? And then there's going to be the new compact discs. Right? So the old records, they were like some different standard sizes, but they were obviously bigger than CDs, right? Compared to like the modern CD. Right? Right? What's the difference in these things? Or does it have to do with linear and angular speeds? Okay. So here's the label he's talking about, like in the middle, the sticker go. Okay. Right, so this is an invention that goes back to Thomas Edison and his team. And what they originally did was they took wax. Actually, it was cylinders was the original design, but they eventually went with this disc shape. Okay. And you take this wax and you take a needle and poke in the wax, have this needle attached to a microphone. Speaking of microphone, it's going to vibrate the needle down, right? Then give this thing a spin, and if it's like melted wax, then that'll leave an imprint. Right? Then, as the record rotates over time, the needle moves closer and closer to the center. Right? And then the wax dries, and so now you have a solid record. Right? Then go back, hook a different needle to a speaker. Right? And then this thing vibrates up down, and then you get the sound back. So that's the basic principles of how the analog recording works. Right? Now, this record would be spinning at some constant omega, some number of radians per second, right? Or revolutions per minute, you think like that. Right? Now, let's say, because I want to think about what's going on with the linear speed v between the needle and the surface, right? So just to simplify this a bit, let's suppose that it makes 1 revolution per second. You guys manage that? Like 1 revolution every second? Okay. Now, if that's true, then out here on the outside, say the first track is playing, right? Doesn't move a really long distance in that second versus on the inside track, let's say the very last minute of the very last song was playing, right? It only goes a little tiny distance in the same amount of time, right? So that's a variable linear speed between the needle and the surface of the disc, right? And that speed slows down over the course of the record, right? From outside to inside. Okay? Right. Now, in more recent decades, along come these compact disc CDs, which are digital. Right? And when the engineers were putting these together, they were considering this. They can consider the information density that would be associated with the analog style records, which is that 1 second of a song might take up a lot of track near the beginning, but not very much track at the end. So the information density actually was also variable, just like V was. But for a CD, if you're thinking about like bits, you got bit, 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 and on the outside it's like bit, 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 right? Each bit contains some amount of digital data, like a 0 or a 1, right? There's a laser that's reading it, and the laser actually goes outside to inside. That's kind of a trivial difference between the old records and the newer. So it goes outside to inside, or sorry, inside to outside. So if you like chip your CD on the outside or scratch near the outside, you can play the first 2 tracks, but not the last 2. Right? So I would say, hey, these 5 bits, same amount of information, same amount of like linear space, but look at the angular space. There's a lot of angular space taken up on the inside, and hardly any at all near the outside. Right? So in terms of like a linear speed between the laser and the surface of the CD, there's actually a constant linear speed between the 2. Right? But to achieve that, you actually have to do something really tricky. And that's that the disk actually has to slow down going from the inside to the outside. Right? See like the first track to hit all these bits has to spin really fast, but the outside has to spin like hardly at all. Right? So there's now a variable omega, and then outside to inside, the disk actually slows down its rotation to play the song, extract that information from the CD. All right. Let's look at your guys' last couple of homework problems, because we actually finished most of these. We just got a couple left of the main assignments. Right? And then actually some of the bonus questions and some of the questions that I didn't assign at all, I do like a lot too. So I don't know, we might look at some of those next week, but we just got 2 last ones here. So number 7, and this was like a test question at the end of the book. I just like this question a lot. Right. You use a 25 centimeter long wrench to remove the lug nuts on a car wheel, as shown in this illustration below. If you pull on the end of the wrench with the force of 2.0 times 10 to the 2 Newton. Okay, pause right here. Guys, that is scientific notation. You guys know that, right? What's probably the more colloquial way to actually write that number? How many newtons is that?
200.
200! Yeah, 200. Because times 10 to the 2, that's 2 decimal places, 200. Right. Now, the advantage of writing it specifically this way is it actually does convey one more piece of information that just the plain number 200 does not. What can you extract from scientific? The fact that it isn't scientific notation also tells you what? Yeah, exactly how many digits are significant. Yeah, you guys hear what Josh was saying? Okay. So, like if I just wrote out the number 200, you wouldn't know. See, 2.0 times 10 to the 2. I know that this 0 specifically is significant, right? But not necessarily anything after that. So this might actually be anywhere between 195 and 205 newtons, right? It's kind of a ballpark play. It might be 202 newtons. Something like that, right? Okay, we also have this angle of 30 degrees, like they're showing exactly in that picture. What is the torque on the wrench? Torque on that wrench. Right? Right, so I know that torque is R cross F. So see that as a starting point. Right, torque is R. Oops, back up right here. Right, torque is R cross F. Right. And the radial size of this is 25 centimeters. Sorry, one more middle step. Right, cross product. Remember that means that you're going to multiply the magnitudes of these vectors. These are all vector quantities, right? Vector. Right? So R times F times the sine of the angle between them. Or another way to shake that is it's just the perpendicular component between the two, right? Only the perpendicular part actually does anything. Right? There's a component of this force that's aligned with this dashed line that actually causes any torque, any rotation. Okay? Right, so we got a radius of 25 centimeters. We got a force of 2.0 times 10 to the 2 newtons. You guys told me that's 200 newtons, right? Okay. Again, see how it's ambiguous as to which zeros are significant? But scientific notation, you know that one is significant and that one is not necessarily. Right? Okay. Then times sine of the angle between them. Now, here's where you got to be careful, right? Because the angle they listed is 30 degrees. Should 30 degrees go there? Yes or no?
No.
You're right. Yeah, no, right. Because think about this. Let's play around this angle in our minds. Right? Imagine like an animation. What if you took this all the way to 0 degrees so that it was exactly aligned with that dashed line? Right? 0 degrees from that dashed line. Right? Wouldn't that mean that these two vectors were exactly perpendicular? Right? Speaking of which, I meant to mention on your guys' quiz, there's a similar question, number 2. These are supposed to be perpendicular. They were perpendicular on my computer screen. Then I printed out, everything kind of squashed a little bit, but assume that those are perpendicular. Okay? Pretty close. Okay. Okay, but if I typed in that number exactly, then that would be sine of 0 degrees. But what is sine of 0? It is 0. Huh. So that might be a hint that maybe that angle actually should not go there. Okay? But I could figure that out anyway, so that it's not going to be that. Okay? So if this angle is 30 degrees, what angle should actually be punched into this formula? What angle is this right here? 60 degrees. Yeah. Okay, so the angle between this force and this radial arm is actually 60 degrees. Okay. Alternatively, if you wanted to use the 30-degree angle, you could with a cosine. Although so could say cosine here, but you have to consider what angle am I talking about. This angle is the angle between the two vectors. Right. So let's do that. We got 25 centimeters times 200 newtons times sine of 60 degrees. So I'm looking at a torque of 4330, and this would be Newton centimeters, right? Like that torque. Okay. Your guys' lab yesterday, your torque lab, you were measuring newtons and centimeters, and your torque values were also in Newton centimeters. So you can think about what you did yesterday, look at this number. Oh, okay. Yeah, compare that. Okay. Okay. Now, a couple other things. Let's actually change this to Newton meters. How many Newton meters is that equal to? Well, centi. Guys, how many cents in the dollar? 100. So should I just roll the decimal back 2 places? Right? Like 43.3 Newton meters. Okay. And then, last detail is, well, let's go back and look at the numbers that were actually given to us. 25 centimeters, 2.0 times 10 to the 2 newtons, 30 degrees. How many significant digits do we have to work with over and over again? I see 2, right? There's 2 sig figs there, 2 sig figs here, like very expressly written out. Okay. The angle, 2 sig figs, right? So, do I know that this 3 behind the decimal place is actually a 3? Maybe it's a 2 or a 7. I don't really know, right? So again, like 200 newtons, that might be 196. That might be 201 newtons, right? Or this might be 25.1 centimeters. So I know I don't talk about sig figs very often. That's why I want to make a side note to bring it up now. Right, so as much information as you actually know is you could say like 43 newton meters, right? To 2 sig figs, 2 significant figures. Okay, there you go. That's the answer. All right, and last one, number 88. If you happen to be leafing through your book and trying to find this problem, number 88 actually comes from the next chapter, chapter 9. I wanted to find a question that had to do with angular momentum, which this question does. Yeah, some places your book is kind of light on the information, so and also those chapters in a kind of a weird order. So anyway. From chapter 9, number 88, gymnastics. We're looking at a gymnast performing a routine. First, she does giant swings on the high bar, holding her body straight and pivoting around her hands. Then she lets go of the high bar, grabs her knees with her hands in a tuck position. Hey, wouldn't that be like bringing her mass distribution like closer to the center? Hey, you guys remember those 2 meter sticks I passed around class a few weeks back? Right? One had masses really far out, kind of looks like this. One that had close in, looks like this. So already I'm thinking this might have something to do with rotational inertia. Something to do with that. So finally, she straightens up and lands on her feet. And in this very last picture where she's planted, looks like she's kind of distributed like when she was swinging around the bar, but she's still crouched a little bit. Right? So maybe close to this, but somewhere between these two, right? Kind of like a middle. Okay? Middle rotational inertia. Right? All right, so 3 parts, ABC. Part A, in the second and final parts of the gymnast routine, what axis does she actually spin around? What axis does she spin around? Well, that is around 88. Okay. You guys probably know the answer, but just in case you're thinking about it, right? We're going to give you guys a similar type question. What if I took this pin and I went, and just threw this across the room, and it starts tumbling like this, as it's flying through the air, right? So I got this pin, and it goes into a projectile motion as it's spinning. And projectile motion, that would make a parabola path, right? That's like spinning. Right? Which point on the pin is actually following this projectile path? Because it's not every point, it's only one point, and that's which point on the pin? Yeah, the center of gravity, the center of mass, okay? Which is the same point that you could balance on your finger. So right about there. There's the center of mass right there. Okay? Tomorrow, I'm going to have you guys do an activity that's related to this. Right, so that's the answer to part A. Is she's actually going to rotate about her center of mass, right? Which is pretty close to your belly button. Pretty close. Part B, rank in order from greatest to least her moments of inertia in the 3 positions. Okay. Well, remember how originally her mass was distributed really far out away from her center of mass? In the second frame, it's all tucked in really close. And in the third frame, probably somewhere in the middle. Right? So I'm thinking that the rotational inertia in the first frame is the greatest. I'm thinking that in the very last frame, it's kind of in the middle. And in that second frame, it's as small as it's ever going to be, right? When she's tucked in, she has the smallest rotational inertia. And part C, rank in order from greatest to least her angular velocity in each of the 3 positions. Angular velocity. Right? Well, this is where conservation of angular momentum kicks in. So here, I'll set up some omegas. Omega, because omega is angular velocity, right? It's like her spin rate, radians per second. How fast is she spinning? Okay. Now I'm going to put some subscripts, 1, 2, 3, but we got to figure out which is which. And the way we're going to figure that out is with conservation of angular momentum. Let me spell this out because this is a variable that we don't use very often. You don't see this very often. So conservation is that equal sign, right? So before equals after, right? Angular momentum, right? So momentum, but in a rotational sense, right? That's what capital L is. Right? Now, do you guys remember what linear momentum is? It was P equals what times what? Just for linear momentum. It's mass times velocity. You guys remember that? Mass times velocity, right? Right. So for angular momentum, what are the rotational equivalents of each of those variables? Instead of mass to represent inertia, now we've got I, rotational inertia. And instead of V, velocity, we're going to have omega. See how this is analogous to mv, right? I times omega. Right? So this is before equals I times omega after. Right? Now I said sum of, like you get lots of bits, but we only have one person in this case, so it's just I times omega. Right? Hey, you know what this equation is the same as? This is the same as the ice skater question. The same as, you guys remember Paul Hewitt on that turntable? Yeah, those masses really far out. He went into a slow spin. Okay, so he started off with a very large I value and a very slow omega, spinning very slowly. Then he did some work to pull those weights in. That changed his I value, made it very small. But to compensate, remember the omega had to increase so that the product would be the same. For example, suppose this number was like 6 and 4, and then it goes down to like this crashes down to 3 units, so kilogram meter squared, whatever. Right? What does final omega have to be to balance that equation? 8. See how if I is half as much, omega has to be double, right? So, right? Guess that? Okay. So go back to this question then. right? Omega. Okay. Maybe the picture is a good place to look at. Right? So which one would she be spinning the fastest? Which frame? First, second, or third?
Second.
Yeah, definitely the second frame, right? So spinning the fastest right there. Right? So frame 2 is definitely going to beat everything else. Right? You know what? Actually, I guess there's a couple ways you could interpret the end of this. Right? So if that third frame, if you assume that she hasn't quite hit the ground yet, then that would still be the middle step. Right? But if you assume that her feet are planted, let me go back and read the question again. Finally, she straightens up and lands on her feet. Tell you what, let's interpret it this way, just because it's closer to the pure physics. Let's say that at frame 3, let's say she's 1 millimeter above the ground. Okay, so she's still rotating. She's about to go in for the land, okay, but she's still rotating because she's still in the air. Okay, and if you assume that, so she hasn't quite landed, she's just about to. Okay, then would this be the middle omega? And then when she was spinning on the bar and had the greatest rotational inertia, she would have had the least angular velocity. Okay? Using this interpretation. Okay. Now, if you had the interpretation of she's actually planted into the ground and come to a full stop, then omega 3 would be the least because it would actually be 0. Okay. Guys good? All right. So that's all the main homework problems. Like I said, I like some of the other ones too, so might look at some of those another time. But I want to ask you guys some other stuff. All right. I want to do a little bit of review and hit some other points that was cool enough. Okay. So actually, sort of related to that, I think I may have asked you guys this question or something really similar back in the day. Okay. Suppose you have an incline. We're going 3D with this. Okay. And I've got 4 different rolling objects at the top. I've got a bowling ball, like a solid cylinder. I'll have maybe like this lab weight right here. Solid sphere. Okay. This could be basically a solid cylinder. Okay. So draw a solid cylinder. Okay. Let's have a basketball, which is like a hollow sphere. Okay. And finally, a ring, kind of like your O'Neill cylinder, okay? Right, where all the mass is distributed at the end. Okay? And let's say there's some static friction just to do some rolling. These are all going to roll to the bottom. Okay? Now, if it weren't for the rolling, you guys remember one of the very first labs I ever had you guys do with Hot Wheels cars. You're like, okay, well, they all go to the bottom at the same time. Okay? But the fact that their masses are distributed differently and they are rolling, that means that, well, somebody's going to win the race to the bottom. They put like a finish line banner at the bottom. Right? Somebody's going to win this race, right? And somebody's going to be moving the fastest. Right? Whoever wins the race ends up also be moving fast to the bottom. Right? So it has something to do with rotational inertia. Right? Let me see if you guys know this or remember this or are able to figure this out. Who's going to win the race? And I'll tell you what, I'll narrow it down to one of these two. It's either the bowling ball or the ring. Okay, the bowling ball or the ring. Now think about how the masses are distributed for each of those, and what kind of energy might go into making it rotate. Okay. Show of hands. How many of you guys think that the bowling ball wins? Who says the bowling ball is going to win the race? Who thinks the ring is going to win the race? Okay, so got a few votes on each one of those. Right. Let's think how you could approach this. Right. So let's look at some rotational inertia values. This is from page 206 in your book. See, for a ring, it's just plain mr squared. Remember, for a point, it was mr squared. It's just a series of points as a ring. Okay? For a cylinder, well, some of the mass is distributed closer to the center. The net effect is 1/2 mr squared. For a bowling ball, it's 2/5 mr squared. And your book doesn't list the basketball, but that one's 2/3 mr squared. Right? So let's look at some I values. I equals mr squared. We got 2/3 mr squared, 1/2 mr squared, and 2/5 mr squared. where R refers to the radial size of each object. Now, I will let you guys say, I'm not going to solve this whole thing for you. I just want you to see the big picture of how she solved this and then how to navigate who's going to win. But I will let you guys know that the mass and the radial sizes do end up canceling out. So even if they're different masses and different radial sizes, that has nothing to do with the answer. The answer has everything to do with how the mass is distributed, which is like these fractions in the front. You can solve this with conservation of energy. Guys, what kind of energy do these have at the beginning? Potential. Yeah, there is some elevated height, right? Or if you want to make it a little trickier, this length, this angle, L times sine theta is H. Right? And then at the bottom, something to do with kinetic energy, but it's actually two different kinds of kinetic energy. So you can say sum of energy at the top equals sum of energy at the bottom. Right? Now at the top, it's exactly what you guys just told me, mgh, potential energy. At the bottom, they're going to be in motion, so something to do with 1/2 mv squared for each one. But also, some energy goes into making it rotate, 1/2 I omega squared. Okay? Okay. Now, this I is some function of m, which means that this I and this m, well, this m is embedded in this I somehow. Okay? And this omega is related to this v. I know what this omega is. It's equal to v over r. So this and this are related. This is some version, I'll say proportional to mr squared. So these m's can be related. Okay? This is the setup to solve this, and then you can like solve for v or something like that. All right, now that's as far as I'm going to show you, except that I'm going to do one more thing. I'm going to switch my screen over. See, present screen to share. All right, just show you guys that I've worked this out ahead of time. So different Rolly objects like that hollow cylinder, solid cylinder, solid sphere. I think I left off the basketball, but anyway. Hey, look, conservation of energy setup, chug, 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 substitutions. And at the end, you get V equals. And notice it's different V's. It's proportional square root GH, but something different times each one of those, right? But look how the bowling ball, the solid sphere, has the fastest speed, right? You guys see it's the fastest speed? Okay, so it's going to be going fast to the bottom. Got there first. Actually, there is one thing that would even beat the bowling ball, and that's if you had a block on a frictionless incline, because now the key for this one would be frictionless. That would be different. But the key there is that none of the energy would go in to make it rotate. So it all goes into translational speed. And that one is exactly square root 2gh, which is something that you guys have seen recur over and over in this class. That's sort of like the upper boundary limit on how fast it can go. Right? And all these numbers are a little bit less than that, but the bowling ball beats all the other Rolly shapes. Okay. All right. Back over screen. Let's look at... Okay. I'm going to do a rotational kinematic question with you guys. Suppose you have a rotating turntable. Okay. And let's give it an initial angular velocity of, let's say 100 radians per second. Okay. And let's say that the time to come to a full stop is like 5 seconds. Okay. Can anybody tell me how far it would have spun through, like how many radians it would have rotated through? Let me give you guys a head start on that. Can you guys figure out how many rotations that would have made? Here's a hint. It has something to do with these rotational kinematic formulas that are on that poster on that wall.
We're trying to find Toy Story.
Okay, you're trying to figure out. Okay, so here's the premise. It's spinning 100 radians per second, which is actually really fast, right? It's going every single second. It's turning 57 degrees times 100, right? So, or think of it this way: what's 100 divided by 2 pi? It's making almost 16 complete revolutions every single second. Okay? But then you let it go. Maybe there's some friction, and it slows to a stop in 5 seconds. how far would it have turned in that time? How far? Right? So I'm going to solve this with a, here, I'll make a tax VV table, but the rotational equivalence. So time, alpha, theta, omega initial, omega final. Okay. So okay, seconds, radians per second squared, radians per second, radians per second. Okay. And I know this number is 100 radians per second. Oh, you know what I meant to do was give you guys revolutions per second. How do you guys convert it? But okay, let's say sort of did that already. It's going 15.9 revolutions per second. Right, so that converts to 100 radians per second. Okay, so we got that. We know final omega has to be 0 radians per second. That's what stopping is. Okay? And that all happened in 5 seconds. Okay? And the question is, can you figure out how far did it rotate? Okay? Well, to answer that, first of all, it's looking a lot like the second equation. Well, except the problem is that there's no theta there, but there's an alpha, and that's the thing. You got to solve for alpha first. These all have an alpha in them, and alpha is the rate that it's changing its angular velocity. In this case, it's slowing down. Alpha's got to be a negative number. So let's do this. Let's start with that middle equation, get alpha, answer that question first, and then go back later and solve for theta. So final omega is equal to initial omega plus alpha times t. Right? Analogous to v final equals v initial plus a times t. This is going to 0 radians per second from 100 radians per second. It's slowing down at some rate we're trying to figure out. It does this all in 5 seconds. You guys see I'm going to subtract this over and divide by 5? Okay. So alpha is negative 100 divided by 5. Isn't that negative 20 radians per second squared? Right? Okay, so this is the rate it's slowing down. Right? Okay. And once you got that, okay, now we can go to one of those other kinematic equations, like either the first or the third, but I'm going to pick the first one because it's already set up to solve for what we want. Theta equals omega naught t plus 1/2 alpha t squared. Right. And we've got, I know omega naught was 100 radians per second. The time interval was 5 seconds. Okay. Now, if it wasn't slowing down at all, suppose it just kept constant angular velocity, that would be the answer. You'd be like, okay, well, 500 radians. But the fact that it's slowing to a stop, I bet it's going to be less than that. Okay. So plus 1/2 times negative 20 radians per second squared, all times 5 seconds being squared. Okay. So let's see, 100 times 5 minus 1/2 times 20 times 5 squared. Looking at 250 radians, and that is the answer, 250 radians. Okay. Okay. Guys get that? Okay. I wonder how many revolutions that is. Well, I know there's 2 pi radians per 1 revolution. Okay. So it's 250 divided by open parenthesis 2 pi close parenthesis. That is the same thing as 39.8 revolutions. So it turns around almost 40 times in that time interval. Okay. You know what? That was like a 2-step problem, right? Just to figure out how far it spun. First, we had to figure out alpha, and then turn around and solve for theta. Okay. I wonder if maybe there's a more direct way to solve it with a graph. Let's do exactly what we just. Let me throw up the initial question. Let's solve this with a graph. So to do a omega versus time graph, show you guys there's actually a real quick solution from this point of view. Omega and radians per second versus time and seconds. First of all, can you guys draw the graph before I do for that scenario that we just did? Okay. For actually this right here, all you need is this information. Can you plot this information on those set of axes? Give you guys a head start. Did you guys say that at time 0, it was spinning at 100 radians per second? And after 5 seconds, it went to 0 radians per second? And as long as it was slowed down uniformly, that would make that shape, wouldn't it? Right? Isn't that exactly the graph of the scenario we just said? Right? And what property of this graph tells you how far it's spun in radians? Here's a hint. If you want radians, take a look at these units. Got radians per second, got seconds. What is radians per second times seconds? Well, it's radians, which is what we're looking for. Ah, is that something to do with the area under the curve? Something to do with the area of that shape? And what is the area of that triangle? Well, I know it's theta, but it's 1/2 base height. So theta is area of the triangle, 1/2 base of 5 seconds times the height of 100 radians. 500 divided by 2. Oh, that's 250 radians. That's the same thing as we got with those equations. But with the graph, maybe it's a bit faster way to do that. Okay, it's the same thing. It's good. All right, I got one last pair of questions for you guys today. All right, let's review O'Neill cylinder. Suppose we got this O'Neill cylinder. It's spinning about this central axis right here. Okay. Got some omega, and that's going to be the first of 2 questions. Okay. What if I told you that the diameter of this thing is, the diameter is, say, 80 kilometers. So big old O'Neill cylinder, right, rotating out in space. Okay. How fast do you have to spin this thing so that all these people feel like they're in Earth gravity? So I'll say gravity artificial is, well, let's run, it'll be 9.8. 9.8 meters per second squared. Okay. How fast does this thing have to rotate? Okay. The follow-up question is going to be, how long does it take to make one rotation? Okay. Give you guys a hint. Artificial gravity, that's like an acceleration value. Do you think there's a normal force from the ball holding everybody in, acting as a centripetal force? Centripetal acceleration would just be that force divided by each person's mass, which is either v squared over r or omega squared times r. You guys remember this from back in the day? Okay. So how fast does this thing have to spin? Okay. Now, is what got 4 minutes till the bell, so I would normally want to give you guys a little bit more time, but I'm going to play off this one. You guys probably figured that out, at least anyway, right? Okay. I'm going to let 9.8 meters per second squared be the centripetal acceleration, which is the artificial gravity. That's whatever omega is squared times, the radius. Guys, what's the radius of this thing in meters? You guys see 40,000 meters? You guys saw that, right? 40,000 meters. Okay. So I'm going to divide by that and take the square root. So omega is the square root of 9.8 over 40,000. See, meters per second squared, meters. Okay. See what that is. 9.8 on 40,000. This is 0.0157 radians per second. Okay. So that's the spin rate. Okay. Let me say this, divide by pi times 180. Just as a side thought, this is the same thing as 0.9 degrees per second. Okay. So not even quite a degree per second. Like you'd really have to stare at this thing and to see it rotate, right? Because I made it so big. Okay. But my follow-up question, the last one we're doing today, is how long would it take this huge O'Neill cylinder to revolve around once? Right? I mean, I bet it would be in the vicinity of 360 seconds because it's going almost a degree per second. Okay. But let's play off the radian number. Okay. Hey, maybe I can solve this with dimensional analysis, sort of. Okay. I don't think it's strictly a proper way to do it, but it works, so we're going to do this. I'm looking for 1 revolution, which is the same thing as 2 pi radians. Okay. I know it's doing 0.0157 radians every second. And in fact, this is probably going to take a long, long time, so I might even throw in this step, 60 seconds per minute. Okay. Okay. So see 2 pi radians divided by 0.0157. Yeah. Oh, actually, look at that. No, I just picked some numbers randomly, but worked out to pretty much exactly 400 seconds. Divided by 60, that's 6.67 minutes. Or I could call that 6 minutes and 40 seconds. There you go. Right, you guys got any questions today? All right, so good pause point right there, and then tomorrow we'll hit a center of gravity activity.